Our last topic in this section is the comparison test for improper integrals. And the logic behind this test is actually going to be very valuable to us in chapter 10 and 11. So we actually want to pay attention to this. Not that you weren't paying attention before. All right, so it is sometimes easier and simpler to use the comparison test rather than doing all of the by hand work for finding an improper integral. This is, of course, only if you're trying to prove convergence and divergence. That's it, right? So this only proves whether it converges or diverges. That's it, okay? But it's not going to find the convergent value necessarily. All right, so you have two curves. One is bigger, right? One is above the other one. So you can see right here. Here's a curve right here, and it's above this other curve down here. And the logic of the comparison test says, hey, if the smaller function diverges, if this is going to go to an infinite value, then the larger function will, of course, also have to diverge. It'll have to. So if the little one is diverging to infinity, then the bigger one will have to diverge also. And then this is the opposite, this first bit. It's saying, hey, if that bigger one's converging, if that's going to a single number, then there's no way that the smaller one goes to infinity. It would also have to go to a single number, right? It's going to force down that little one. So let me write that up. Of course, when we're noting that the bigger function is the blue one, right? If the blue one is bigger than this one. So this is smaller, g of x is, and this is larger. And we can see it right here. This is the larger function, right? It's above. And then this is the smaller function down below. And that's what they're establishing with that greater than. And again, it's for some constant a. It doesn't have to be true over here. It just has to be from some point a onward to infinity. Okay, number 1 states that if the f of x, which is the bigger function, I'll capitalize it and everything. The bigger function converges to a finite number. Right, that's what convergent means. Right, it converges to a finite number. Then g of x, which is the smaller function, will have to also. Number 2 is saying, right, because the big one's going to force it down, right? So number 2 is stating that if the bigger function, let me go backwards. If the smaller function diverges, the smaller function goes to infinity. If g of x, which is the smaller function, diverges to infinity, or just diverges, heck, it doesn't even have to diverge to this particular number. It can just be looping around. But if it diverges, then f of x, which is the larger function, must also. Now, all of this is predicated on the very important comment that this has to be true. It has to be that f of x is greater than g of x on that interval. Must be true. Right? Must happen. There's something else to notice. I'll just make a note of it here. Just trying to figure out my color. If the bigger function diverges, we don't know what the smaller function diverges, or what it does. Right? If this bigger function goes off to infinity or something, Okay, well then g of x may go off to infinity with it, may go down to 0, could go to 3, we don't know, right? We don't know. So if the bigger function diverges, so it follows a very particular pattern. You have to have the bigger function converging, forcing the other one to converge, or the smaller function diverging, right? But if the bigger function diverges, nothing, you got nothing. And similarly, if g of x, which is the smaller, converges. So these are if-then statements that really matter which one's going where, right? If the smaller function converges, nothing is known about the bigger function. Right? So there's 4 cases, if you will. 1 and 2 are the ones you want. If the bigger one converges, the little one will too. If the bigger one or smaller one diverges, then the bigger one will too. But this one and this one are useless to us. This is, if you will, case 3 and case 4. They're going to come back and haunt us, all 4 of these cases, in the next chapter, in chapter 10. Right? So be warned, right? So these ones are useless. These 2 are the ones we want. So these are good, and these are bad. These will get us nothing. All right, so let's do an example and see if we can make any kind of sense of this. All right, so we have a request to use a comparison test to determine whether the function 1 to infinity of e to the negative x squared dx converges. So let's look at 1 over e to the negative x squared, which is right here. So there it is. Isn't it beautiful? So e to the negative x squared is that function right there. And so then I can graph, not there, to that piece. Now one can reasonably compare it to, let's think, e to the negative x, because I already know that e to the negative x converges. I can prove it, right? So that's not hard to prove. So I'll make a comparison to e to the negative x, and if this blue one here, if this one, let me turn this one off. If this blue one here converges, then that'll force the smaller one to converge also. See the logic? Right? In other words, if that blue zone is a number, then the green zone is going to have to be a number. You don't know what number it is, but it's definitely going to have to happen. All right, so let's start by proving from, what was it, from 1 to infinity is convergent. So I'll just put convergent. All right, prove convergent. Okay, so the integral from 1 to infinity, here, let me stick with my color choices here. Give me a second. Because I want to prove convergent for the smaller, or for this larger function, this one right here. So that's the larger piece. It's not large at the beginning, but it is larger at the end, and that's what matters. The fact that that curve is above the other curve for the tail piece. All right, so the integral from 1 to infinity of e to the negative x dx is equal to the limit as b goes to infinity of the integral from 1 to b of e to the negative x dx, which is equal to the limit as b goes to infinity of negative e to the negative x, because I know how to integrate that from 1 to b. Oh my goodness, which is the limit as b goes to infinity of negative 1 over e to the b minus a negative 1 over e to the negative, or e to the 1, sorry, I'm putting it in the denominator. So I'm doing 2 steps at once there. I'm substituting and I'm putting the negative power into the fraction form. Okay, now if I put infinity in, let's think about that. This would be 1 over e to the infinity. So this is 1 over infinity, which means that this is 0. So that means that I have 0 minus a minus 1 over e, which is 1 over e. So this is convergent. I've proven convergent. Okay, I proved convergent. Now I need to prove that e to the negative x is less than or equal to e to the x. which means e to the negative x squared is less than or equal to. So g of x is e to the negative x squared. That is indeed less than e to the negative x. And you can see from the graph, right? Because I have my e to the negative x squared right here. And you can see, oops, I went off the rail there. There we go. From 1 on, this is a smaller graph, right? From 1 to infinity. So I guess I should say, on the interval from 1 to infinity, this is true. And therefore, since the blue one converges and we know it's larger, that means that g of x converges also. You have to have two pieces. Well, three. You need to have another function to compare it to. You need to have this piece right here where you prove convergent. Then you need to have this piece right here where you prove that the other one graph is smaller than the other one. And then you have your final result. And this is bugging me. Part 1 is really the proving convergent part. So part 1 is prove convergent. Part 2 is prove the less than or equal to, right? That f of x is, or g of x is less than or equal to f of x. Like that. And then part 3 is your conclusion.